Download this code from codegive.com, link in the description below. OK, let's dive into signal flow graphs, SFGs, and work through a solved problem with a code example to help illustrate the concepts. I'll provide a detailed explanation of each step. What is a signal flow graph, SFG? A signal flow graph is a graphical representation of a set of linear algebraic equations. It's a visual way to analyze and solve complex systems, particularly in control systems, signal processing, and circuit analysis. SFGs are closely related to block diagrams, but they offer a more concise and powerful way to determine the transfer function, the relationship between input and output. Key components of an SFG*. 1. Nodes. Vertices represent variables or signals in the system. Each node has a value associated with it. 2. Branches, edges, directed lines connecting nodes. Each branch has a transmittance, gain, associated with it, representing the multiplication factor between the signal at the source node and the signal contributed to the destination node. 3. Source node *, a node that has only outgoing branches. It represents an input to the system. 4. Sink node *, a node that has only incoming branches. It represents an output of the system. 5. Path *, a sequence of branches traversed in the direction of the arrows, with no node being traversed more than once. 6. Forward path *, a path from a source node to a sink node. 7. Loop *, a closed path that originates and terminates at the same node, with no other node being traversed more than once. 8. Non-touching loops *, loops that do not have any nodes in common. Mason's gain formula, the key to solving SFGs. The core of SFG analysis is Mason's gain formula, which provides a direct way to calculate the transfer function of a system from its SFG representation. Where *t, the overall transfer function, example output/input. *delta, the graph determinant, calculated as delta equals 1, sum of all individual loop gains, plus sum of gain products of all possible combinations of two non-touching loops, sum of gain products of all possible combinations of three non-touching loops, plus *pk, the gain of the kth forward path from the input node to the output node. *delta k, the cofactor of the kth forward path. This is the value of delta for the part of the graph that does not touch the kth forward path. Essentially, it's the graph determinant calculated after removing the kth forward path and any loops that touch it. *sigma, the summation is taken over all forward paths from the input to the output. Solved problem 4, a detailed example. Let's consider a signal flow graph represented as follows. Here, *x1 is the input node. *x4 is the output node. *a, b, c, d, e, f are the branch transmittances, gains. Goal * find the transfer function t equals x4/x1. Steps * 1. Identify forward paths *. Path 1, x1-x2-x3-x4, gain p1 equals a *b *c. 2. Identify loops *. Loop 1, x2-x3-x2, gain L1 equals b *e. Loop 2, x2-x2, gain L2 equals a *d. Loop 3, x3-x3, gain L3 equals c *f. 3. Identify non-touching loops *. Loops L2 and L3 are non-touching, they don't share any nodes. The product of their gains is L2 L3 equals adf. Loops L1 and L2 touch each other. Asterisk loops L1 and L3 touch each other. 4. Calculate the graph determinant, delta. 5. Calculate cofactors, delta k. Asterisk 4. Forward path 1, P1. This path touches all the loops, L1, L2, and L3, so by definition, the area of the graph that does not touch P1 is empty. Therefore, the cofactor delta 1 equals 1. 6. Apply Mason's gain formula asterisk. Therefore, the transfer function of the system is T equals ABC slash 1, B plus add plus CF, plus addf. Code example, Python. Here's a Python code example using symbolic computation, SymPy, to calculate the transfer function. This makes the code very readable and closely reflects the mathematical formula. Explanation of the code asterisk. 1. Import sympy asterisk. This imports the SymPy library, which is used for symbolic mathematics in Python. 2. Define symbolic variables asterisk. We define the variables a, b, c, d, e, and f as symbolic variables using sp symbols. This allows us to work with them algebraically. 3. Calculate the graph determinant, delta. The delta variable is calculated according to the formula we derived earlier. 4. Forward path gains and cofactors asterisk. The forward path gain, P1, and its cofactor, delta 1, are calculated. 5. Mason's gain formula asterisk. The transfer function T is calculated using Mason's gain formula. 6. Simplify, optional sp simplify, T, attempts to simplify the expression, which can make it more readable. 7. Example usage asterisk. The code demonstrates how to substitute numerical values for the variables to get a numerical result for the transfer function. This is done using the .subs method of the SymPy expression. How to run the code asterisk. 1. Install SymPy asterisk. If you don't have SymPy installed, you can install it using pip. 2. Save the code asterisk. Save the code as a Python file, example sfg_example.py. 3. Run the code asterisk. Open a terminal or command prompt and run the script. The output will show the symbolic expression for the transfer function and the numerical value after substitution, if you use the example usage. Key takeaways and general approach asterisk. Asterisk. Draw the SFG asterisk. If you're given a set of equations or a block diagram, the first step is to accurately draw the signal flow graph. Make sure to label all nodes and branch transmittances. Asterisk. Systematically identify paths and loops asterisk. Carefully identify all forward paths, individual loops, and non-touching loops. This is the most error-prone part of the process, so double-check your work. Asterisk. Apply Mason's gain formula asterisk. Use Mason's gain formula correctly to calculate the transfer function. Asterisk. Simplify, if possible. Simplifying the expression can make it easier to understand and use. Asterisk. Use symbolic computation asterisk. Tools like SymPy, Python, or similar libraries in other languages can significantly help with the algebraic calculations, especially for more complex SFGs. Advantages of using SFGs asterisk. Asterisk. Systematic approach asterisk. Mason's gain formula provides a structured way to find the transfer function. Asterisk. Visual representation asterisk. The graphical representation helps visualize the relationships between variables. Asterisk. Handles complex systems asterisk. SFGs can be used to analyze systems with multiple feedback loops and interconnections. Limitations asterisk. Asterisk. Linear systems asterisk. SFGs are only applicable to linear, time-invariant systems. Asterisk. Complexity asterisk. For very complex systems, the process of identifying all paths, loops, and non-touching loops can become tedious. In summary, signal flow graphs provide a powerful tool for analyzing linear systems. By carefully drawing the SFG and applying Mason's gain formula, you can systematically determine the transfer function of the system. The combination of the SFG technique and a symbolic computation library like SymPy provides an efficient and reliable method for solving complex problems. Remember to practice with various examples to become proficient in this method. Good luck.